In this series of videos we'll be taking a look at this. It's a ZAX ICD178 for a Z80. It's an in-circuit emulator. It's intended for systems hardware development, software development, and this came out back when the Z80 was in fairly widespread use in new systems, and it's a fairly complex in-circuit emulator. Allows quite a few different functions to be performed on the system that you're developing, and we'll look at those functions in more detail in a later video. Before we start that, a bit of background on this and why I decided to show these particular videos. I wasn't going to show this repair, but I happened to see a comment on a forum a few days ago that prompted me into deciding to include a video series on this. Now, I was intending to make a series using this device, but really it was going to be about using it and developing some Windows software to control it. But as I said, I saw a comment on a forum, and I think it's probably the silliest comment I've ever seen on any forums, and just a bit of background on what this is all about. I don't normally look at forums too much. They seem to be more a never-ending series of arguments that bear little relation to the question that was originally asked, and so I tend to steer clear of them. And in this instance I was actually looking for a manual for this. I don't have a manual for it, and I came across a comment that basically said that don't use Z80s, get a Raspberry Pi. And looking through the comments on that forum from the same person, it was clear that he'd never done any systems development, because his comment was basically, you do not need an in-circuit emulator because Z80s are so simple. You'd have to be a drunken monkey to make a mistake writing software using a Z80. Clearly somebody that's grown up in the social media era, where it's really a case of the blind leading the blind. Someone who clearly has never developed any hardware systems, and certainly has no understanding of how much more difficult it was developing systems back in the day when the Z80 was at the forefront of many systems development. In fact, the first development project I ever worked on of any significance, we were developing, it was an embedded system for medical use. It had up to 256 simultaneous RF data channels, Ethernet, RS-232, graphics display, keyboard, memory data storage. It was a very complex system, but we did not have an emulator. And I was developing it pretty much alone, and to develop it, what I was using was one-time programmable devices, and you're probably not familiar with those if you got into development fairly recently. And they are basically devices that you program like you would a modern device, but you couldn't erase them. Once you programmed it, that was it. You couldn't change it. If you made a mistake, it was scrap. They cost around £40 each, and that's equivalent in today's money of about £105. So each time I wanted to do a build and test, it cost over £100. Systems like this cost about £7,000 at the time, so it was about 70 devices worth. So if you were going to do more than 70 test cycles, it was actually more cost effective to buy a system like this. As I say, I'll go into all the details of exactly what this system can do later on, but like I said, the comment clearly had no understanding of quite how useful a system like this can be, because when I moved on to another project, we were using 68,000 processors, and we finally got our hands on an emulator. Now, before that we ended up using windowed devices, so like modern EEPROMs, where you can erase them, reprogram, reuse them. So not quite as convenient as an in-circuit emulator, but certainly a lot cheaper because we could reuse the devices. But when we got the emulator, it was an absolute game changer. It makes things so much easier. You can plug it in. Basically, this plugs in place of the processor on your target system. So this is obviously dismantled. I've been working on this for a while. This plugs into a pod that you pull the Z80 out of your target system, plug the pod in its place, and then this entire system takes the place of the Z80. And this particular one you can control either using software on a DOS PC or just using a dumb terminal, which is what we'll have a look at later on in this video. But the difference it makes when you've got something like this in terms of systems development, as I say, it's a complete game changer, and anyone that says otherwise has never done any serious systems development. And on the forum, as I say, it was clear this guy had not done any proper systems development. And this is one of the problems these days, that you'll get things like Raspberry Pis and Arduinos, and it can lead you into a false sense of knowledge, where you think you're developing systems, and although they're fun to play with, I would still recommend getting down into the dirt with something like this, and it will teach you far more than you can get by playing about with libraries you've downloaded for a Raspberry Pi or an Arduino. Nothing wrong with them, but really if you want to learn the basics, something like this is far better. Now, I've got a number of these for different types of processor, but none of them worked when I bought them, and finally got round to deciding I wanted to get them working, really because of the Osborne one I repaired recently, where something like this would have been invaluable, and hopefully you'll see why as I start to explain how this works. But all of them were faulty, and that is fairly typical for in-circuit emulators. They do take a bit of a hammering. They're plugged into systems that may have faults or are being developed, and there could be an issue with it, and they can get damaged. And one difficulty in trying to repair them is the way, for these particular units, is the way they're constructed. So I've got one here that's still assembled, and you can see it's kind of all crammed into this enclosure. But more importantly, all the boards are joined together with a single wide ribbon cable. There's two on here, but on this particular system there's only one. And so the problem is how to go about trying to fault find on this, because as you can see it's very difficult trying to get to any of it. But what you can do, as I've done here, is you can kind of unfold some of the boards, and you can change the order they're plugged in. So single ribbon cable, it doesn't matter what order the boards are plugged in, so I've kind of changed the order of the boards, and then I can kind of flip them open like this and get to the parts I need, and then I've been able to attach my Agilent 1680 logic analyzer, and then I've been stepping through the code. So I downloaded or read the ROMs. On this particular unit there are 3 4K ROMs, so 12K in total. It doesn't sound like a great deal, but the code in these is very highly optimized, and you'll see that as we start going through it. And everything's controlled through the RS232 port, and so what I've been doing with this is trying to figure out how to get it to work. Now unfortunately I don't have a user manual, and yes, I know there are user manuals for the 178 ICDs online, but it's not for this particular unit, and the command set for this is somewhat different. So it's been a combination of trying to figure out what the commands are to drive this, which I've been doing partly by looking at the code, and also trying to fix the issues with it. So it had a lot of hardware faults, and the first thing I did when I took it apart and looked at each board, trying to figure out what each board was. In general terms it's fairly easy to do that, but I was trying to figure out how to go about fault finding on this, because they are quite complex. As an example, you can map, this has got onboard RAM that you can use for running the code in your target system. Not only that, but you can map the RAM in 1K chunks between the target system and the emulator. So in other words, the 1K block from the target system all seems to be 64K continuous memory, but the 1K blocks could either be on the emulator or on the target system. so you can just replace one K block at a time. But that makes it quite difficult to fault find on, because if there's a fault in that mapping, then trying to get the code to do what you expect is quite tricky. But I found 8 64K by 1-bit DRAMs on this board, and that's the board with the CPU on it, so it seemed fairly likely this was the emulator user RAM. On the board on the left, a large board on the left there, it had the EPROMs. That's obviously where the code for the emulator resides. But of course you have an issue here that we're trying to run a CPU, and this is the CPU, the Z80, that we've got this clip attached to, and that's the one that effectively resides within the target system, but it also has to run the emulator. But it needs memory to run, so not only does it need to access ROM, which is fine, it can just be mapped in and out, but you can't map it in the standard way because it has to run seamlessly. So it has to be memory mapped. You can't use it as in-out mapping, otherwise you'd have to write special code to switch between the different banks, and obviously if you're running the code on the target system you can't do that. So there must have been somewhere on here somewhere for scratch pad memory, such as the stack and variables that the emulator uses, and over here there was a 2K by 8-bit SRAM. And so what I did, I attached a clip to that, found parts of the code where the stack was being accessed, used the logic analyzer, and sure enough, when the stack was being written to or read from, that particular device was accessed, so that was clearly the scratch pad memory. These devices will do real-time full-speed emulation and data capture, so there must be some trace memory on here, and the spec said it had, I haven't got a spec for this particular unit, but a similar 178 said it had 2K of trace memory. And one of the boards, you can't see it, there are more boards in here, but one of the boards had 4 of these 8-bit by 2K SRAMs. And because with the trace memory it needs to be wider than the data bus, of course, because it has to capture address bus, data bus, and the control signals. And so it turns out it's 32-bit wide trace memory, and so 4 8-bit SRAMs, 2K each, would give us 2K of 32-bit wide trace memory. So that was clear what that board did. Serial board, the one that we've got down here upside down, that's the serial board, has got a couple of UARTs on it, so it was clear what that was. And then there was just one other board that was used for control and display, which again is upside down. There's another board under here as well for the keyboard and display. So once I got all that sorted out, I could start looking at the firmware that was in the ROMs and try to figure out what the commands were to drive this, and also try to figure out what the hardware faults were. So we'll go over to the PC, have a look at the code, and I'll just quickly explain how I went about trying to unpick it all. So once I'd read the ROMs, I put them all together into a single file, and I tried running them through various disassemblers. And one of the issues with the code in this particular system is it's dotted with quite a large number of text strings, but also a large number of lookup tables. And if you're aware of how the disassemblers work, you'll know that they're very poor when it comes to dealing with those things. So I ran I think 3 or 4 different disassemblers, ended up having to write one specifically for this that would do a reasonable job of skipping over the text strings and lookup tables. Now it still assembles the code within them, but what I was trying to do is at the end of the table I was trying to avoid a situation where 2 or more instructions were merged or truncated, which causes a lot of problems. So I ended up with this file, and really it's a typical disassembled Z80 file, and the next question is how you go about dealing with this. And so the first thing I do, just as a starting point, is I will go through and search for all return instructions. So if we do a search for return, then you notice we get a return instruction, and what I will then do is put some spaces after it. And the idea here is I'm trying to identify specific blocks of code. Now, that's not to say that a return instruction definitely defines the end of a block of code for a function, because there might be multiple returns in it. But it is a good starting point, and I can just do the next one. If it was a return, a conditional return, I would ignore it. That's almost certainly not the end of a function. So keep looking for return only. And then I went through the entire file and did that, and you end up with blocks of code that may or may not be functions. But chances are some of them are. The next thing I did was to use a combination of the scope and the logic analyzer to hook up to various devices. So for example, I'd already identified the scratch pad memory. What I could then do is trigger on particular writes to that memory, and that in turn would allow me to figure out the memory mapping for each of the devices. So for example, if I monitored the write line for that SRAM and then captured on that with a logic analyzer, I could look at the address that was on the data bus at that time, and that would tell me the address that the CPU mapped that device to. Because obviously a secondary issue here is that while we have 64K of user RAM, it all has to reside within one 64K block, including the ROM and the stack RAM and the trace memory. And it does that in a fairly clever way. It basically divides the addresses by 2. So for example, the 64K user RAM, that's the DRAM, on the CPU board actually starts at 8000 hex as far as the CPU is concerned, and then it's in 2-byte chunks. So from 8000 to FFFF is the entire 64K RAM block with an extra line to determine whether it's the high or low byte within each word. And then everything below 8000 is where the rest of the hardware was mapped. So that includes the scratch RAM, the ROM, the trace memory, all the in-out for things such as the serial. So all that was done in the lower 8000 hex memory addresses. So it's quite clever the way this system works. Once I knew that, I could start doing searches on individual parts of the system. And I then started to tidy this up into what I was identifying as particular functional blocks, which it's taken me about probably 30 hours to do this if I look at the current file. So currently what I have is this is, as you can see, being tidied up quite a bit, and I'm really dividing this into functional blocks. One of the things that had me going for a while was this text at the beginning. Looks like it's a text string, and the instructions for most of these that I could find say that the unit announces itself with something very similar to this when you boot it up. So I spent some time looking for the code that actually uses this to pass it out to the RS-232. Bear in mind that at the time nothing was coming out of the RS-232. But it turns out this appears to be non-functional. It's just here for information only, and it's never actually accessed by the system. So the first thing is the system jumps to this point. Disable interrupt instructions, fairly common at the start of initialization, so that made sense. And then working our way through, there's a lot of addresses that are initialized, and again I started searching for these throughout the code to see what they're used for, and I could do that based on what the code around them was doing. And as I worked through, I was able to identify that some of these are text strings, and also that the system makes very extensive use of lookup tables. So for example, the commands that come through from the RS232 go into a bit of code that essentially looks up a particular command. So this is a lookup table, and the first byte is that's the character that's sent through the RS232, and this is where this system differs from everything I can find online with regard to instructions, because none of the commands, or very few of them, seem to work the way that the documentation is that I can find. If you do have a user manual for this version of the system, it's a ZAX ICD178 for the Z80. If you do have the user manual, then I would appreciate a copy. But back to this lookup table, the first character is the character used for the command, and then the next two characters are the address that that particular handler for the command resides at. So that will then cause the code to jump through to the particular command. So this address here, in this case it's 07D2, is for the A handler, and as you can see we have 07D2, and that's unscrambled by this bit of code here that essentially gets the incoming data from the RS232, and it looks for the matching command, and when it finds it, if it finds it, it loads the two values for the address from the table, and then it jumps to that particular block of code. And it does so using a return instruction, so it pushes the value onto the stack, and then it effectively returns, which will cause the value to be popped off the stack and used as a destination address. So and there's a lot of code like that through this, where the stack is used fairly extensively, and each of the handlers has its own block of code. Now, that's all fairly straightforward, but where it gets very complex and convoluted is that a lot of the code, and I've done this as well when I write code with limited memory space, is that you have to effectively reuse bits of code within individual functions. So for example, this function here has got multiple entry points depending on where it's being called from. Also, when some of these functions return, the address they return to is one that was kind of artificially put onto the stack, and rather than this being called, the stack was loaded and then a jump was made to the instructions. So when it returns, it doesn't return to the point that sent the code to this point, it jumps to wherever the stack was loaded, or wherever the stack address tells it to jump to. So it's quite difficult to follow code through, and it does that because the disassembler has no way of knowing what the addresses are for many of these destination jumps, because it's runtime value dependent. So it does make it fairly complex to unscramble all this, but after probably 10-20 hours I was getting the hang of how it was coded, and then another sort of 20 hours and I've got to this point where I'm getting a fairly good handle on exactly how the code is laid out, and I can start giving names to the particular function blocks. So that's where I am with this. We'll go back over to the bench. In fact, before we do that, we'll look at so when you start up the emulator, you have this cursor, and as I said, the emulator is fairly powerful. So to show some of the features, what I'm going to do is upload a file to it. So you can upload a hex file. And this will let you load a file directly from a hex image into the emulator, and you can then run that code directly from the emulator. We'll just wait for the file to finish uploading. There are various different modes that you can run the emulator in. Here we're just using the memory within the emulator as the code memory, but this could be uploaded into the target system memory, and you can run it directly from there. So in other words, you can run your test code from RAM rather than having to mess about with ROMs. So now we've got that loaded, we can have a look at it, make sure it's uploaded properly. Let's look at the first 100 bytes, and that is the correct code. So you have to take my word for it, this is the code that's supposed to be there. In fact, you can see here it says ZAX ICD178Z. So this is the actual code that's in the files we were looking at. So this is the code out of the emulator ROMs themselves. So the sorts of things you can do are you can copy the code around. So you have a function such as this. So we can copy from any location we want, the amount we want to copy. So let's say we want to copy 20 bytes, and we're going to copy that to an address of 2000. You can also specify whether you're copying within the emulator, from the emulator to the target system, or vice versa. If we then look at that memory space, you can see we now have the exact same code. So it's very powerful, lets you do a lot in terms of manipulating the code. You can run the system standalone as a simple emulator if you want to write some software, but that's not really where its main power is. Its main power comes in tracing the code through. So for example, let's say we want to single step through some code. What we can do is tell the trace we want a single step. We can examine the current trace settings, and notice now it's saying step trace mode, so this is going to single step through any code that we ask it to. So if we start, also we'll set it to trace all, so it's going to trace and store everything. You can tell it what to store as it's tracing. So now if we look at this, you notice it's also saying it's going to capture everything. And what we can now do is actually start it running. So we'll run it, and then we can tell it the address we want to run from. It's gone and it's executed the first instruction. So notice here we have the program counter at 0000 because that's where we told it to run from. If we hit the spacebar, it's now run the next instruction. Note, if you recall, it was the first instruction was a jump, and it's a jump, as you can see here, to 1D. Notice it's also disassembling the code for us, which I'll come back to in a few minutes. So that first jump to 1D it has done. You can see the program counter has jumped through. These are all the flags, and if we now execute the next instruction, you can see it's going through one step at a time, executing the code. You can just set it off to run at full speed, and then it will capture this information in the trace memory, and you can look at it later on. So we'll exit that mode. Just reset the trace. And we can now look at the data that's been captured. So if we look at, then notice that not only is it showing us the data that was captured, so this is the instruction that was being executed when we ran this, and if you're not sure about this you can go back and have a look. So notice that the instructions that are being executed here, C31000, the actual machine cycle that was carried out, but notice it's also disassembling the code for us. So again, very powerful system in that you can get it to disassemble the code that it's captured. You can run this at full speed and capture code as it runs through the system, and there are many such functions, and some are quite interesting. So if we go into this particular one, this will allow us to do the reverse. We can compile code into the system. We'll just quickly examine the code at the start of memory first. So this is what we downloaded a few minutes ago. Starts off at C3, 1D, etc. But if we want to change this and change the code, we can either directly edit it using numeric values. So let's say we just want to change a single value, and we know what the value is we want. So let's say we want to change this C3. So we enter this command. It's showing us that at address 0000 the current value is C3. Let's say I want it to be 45. We'll now exit and we'll look at the memory in that area again. Notice it's now 45, and then we could go back and run this again if we wanted to, but bear in mind this could either be in the emulation memory or on the target system. But sometimes it's far more useful if we want to be able to write in a standard format. So if you're familiar with writing code for the Z80, then it would be easier if we could just write it in the standard command formats rather than having to remember the machine code values. And you can actually do that if we enter a different command, and again we'll start at the address 0000, or it could be anywhere, and we can now enter specific commands or specific instructions. So we'll start off by entering a NOP, and if we want to enter other instructions, so for example we can do that. If we now look at that memory location again, so notice that firstly we have the NOP at the beginning, it compiled that correctly, but also the next instruction is correct as well. You can disassemble the entire contents, so if you've got some memory in here, maybe you've downloaded or copied the ROM from the target system into user RAM, or you can even save this to the PC. There is a command to save all this into a hex file directly from the target system. You can also have the emulator disassemble it in real time as well, so it will show you the disassembled code that's currently on the system without you having to pass it through an external disassembler. You have access to all the ports. You can individually read and write port values, you can change memory, you can copy memory, you can define areas as being ROM or RAM. You can do this on a target system or within the emulator memory. You can run it at full speed, you can trace the operation at full speed. You can then disassemble what the data is that's being captured. So all in all, a very powerful system. And the intent here was not to really show you the repair of this. I was hoping to go straight on to the Windows software development. So I'll be trying to encapsulate all this in a Windows application to make it even more seamless and functional than it is through the terminal. But hopefully you can see already this is a potentially very powerful system, and anyone that says these don't really have any use clearly has never done any serious development work. If you do want to see more of this, I appreciate I've skipped through this incredibly quickly today, haven't really gone into much detail. I just wanted to give you an overall idea as to what I've been up to with this. Also, I hadn't posted any videos for a couple of weeks, so I thought I'd just quickly post this one. But if you do want to see more in-depth information on this particular device, then please leave a comment. But it is one of those very fascinating devices, and I do have a number of these for different types of processors. Some are more complex than others, but they all operate in a fairly similar way and have similar usages. But hopefully you can see this is potentially an extremely useful tool for repairing machines. But hopefully you can see this is potentially an extremely useful tool for carrying out repairs. For example, you could just replace a bit of code on a target system, maybe it's running CPM and you want to do some testing on a floppy disk. You could replace the floppy disk code with some code that's residing in your user memory on the ICD. Change a single instruction or multiple instructions, carry out specific tests, and you can do that at full speed, which is one of the problems in using something like the Fluke 9010A. You can't run it at full speed, so trying to fault find on things like a floppy disk is slightly tricky. But using this system, you can run it at full speed, do proper data capture, and then disassemble the data, all from the comfort of your terminal. So we'll go back over to the bench, have a final look at the device. So as I've been working my way through the code, I've been carrying out various repairs. I found a couple of faulty memory chips. I found some faulty buffers, not really that surprising, it's the kind of thing that does get damaged in these. And also I found some faulty devices on the serial card. Still got a few faults to deal with. Certain functions still don't work the way they should. But what I'm hoping to get across, I'm not trying to pick on anyone by the way, and what I'm trying to get across is that devices like this were incredibly useful at the time that they came out, and I think are still well worth looking at, even if only to use as a learning tool. They are very interesting. Still a bit expensive. If anyone does have one of these they want to sell, then please contact me, or if you have the user manual for this particular version, then again please let me know. But if you want to see more of this, you want to see more of how it works, and working through the logic analyzer to trace various functions, then please leave a comment.